Hi, I am Luke Oxley, a veteran of Team 6498, and in this video I will be talking about FRC Control Loops. To give you a rundown of what I'm going to be talking about, first I'm going to explain what a control loop is, bang bang control, PID control, how to tune a PID loop, feed forward, and motion magic. To start things off, what is a control loop? A control loop is used to modify an output for an input to reach a desired value. Now that might sound confusing, but basically, say we need a lift mechanism to go from point A to point B. A PID loop will let us achieve this. This is heavily used in many axes of any robot that we make, and this heavily simplifies the driving by increasing automation. So many of you might have experience driving a robot where it has a really heavy lift arm, and to keep it at a certain height, you have to continuously kind of bump the throttle up a bit, but then that's kind of annoying if you want to focus on other things. A PID loop lets you say, oh, I want the arm to stay at this position, and it will let it stay at that position. Some of the outputs that we have for a control loop are usually motor power, or say you want your robot to drive straight, it can be like the power difference between the motor sides in the chassis. Some inputs are usually come from sensors, such as an encoder or gyro, or in this picture on the right, this is from our 2020 robot, a camera. Now, one of the simplest forms of control is a bang-bang controller. This is where the output is either on or off. So it's usually used in a flywheel, where if we want the flywheel to go at a set RPM, this will let us do that. So in Bang Bang, if the speed of the flywheel is greater than the desired rate, it'll turn the motor off. Or if the speed is less than the desired rate, it'll turn the motor on. Now, you might be able to tell, but this provides pretty jerky motion, and you should never really use this for slow and accurate movements. Next is the first part of PID control. This is proportional control. And this is where the output to the motor is equal to a constant times its Kp times the error. Now in this is where the output is proportional, hence the name, to the error. And this is usually a pretty simple thing to do, and it works really well for slow-moving applications. Now, some of the fallbacks to proportional control are that your control loop can kind of go out of control and oscillate. You can see in this first graph, we have this line, and all along our set point, we're just going back and forth. This is caused by, first, it's like, oh, we started way far away from the set point, and it rapidly increases and overshoots the set point, and then it's like, oh, I overshot it. And so it just keeps going back and forth, overshooting, and sometimes it just spirals out of control. Now, the other side of this is steady state error. This is one of the more scary ones because you never reach your desired set point. You can see our set point is along this top line, and we always have a gap between our actual position and the set point. So to fix this, what we do is we add integral control. So this is the PI in the PID control loop. This is where the output is equal to that proportional part plus a constant Ki times the sum of the error. Now, this is almost always sufficient in what we're doing. This is the most common of what we use on our team. And for those of you that don't know calculus, integral is just the area under the curve. It represents the accumulated error over time. This is good so that if we have a long undershoot time, where we're never really getting to that set point, it'll be like, oh, we've been at this set error for this amount of time. I'm going to slowly increase our output until we are bumped up to the actual set point. This is really good at eliminating steady state error, but it can increase settling time a little bit. Next is the derivative part. This is now PID. and the output is equal to the P plus the I plus a constant KD times the rate of change of the error. Now we don't really use this that much, but it's used to kind of predict the future behavior of the control loop, and it applies kind of like a brake to our output. And this is really good at preventing overshoots. So it's like, oh, our position is coming in really hot to our set point. It'll apply a brake before we overshoot. So that's kind of what that does. Now, all of this PID stuff is meaningless if you don't know how to tune it, but tuning it is mainly trial and error. There are ways to calculate this with complex formulas, but we usually just trial and error it. First, you set the I and D values to 0, and you slowly increase the P until the system oscillates. Once you know the limits of the system, you lower the P until the oscillations stop. Then you can increase the I if necessary to eliminate any steady state error. Now, when tuning a PID control loop, we always try to include I, especially on really critical mechanisms, because if the robot battery voltage drops and you don't have an I, you'll usually have some sort of a steady state error. And this is bad because then your lift will never really get to that high enough point, or if you're having an autonomous program, your robot will never really follow the right path, and that'll really ruin your match. So always try to include I if you can. Next is what's called feed-forward control. This is where we combine an estimated output value and have the control loop correct for the rest. Feed-forward is where we estimate the set point using known variables about the robot and physics principles. So using formulas, we can account for things like gravity and stuff like that. However, what we can't account for is things like friction and maybe even hitting into another robot. That's where the control loop will correct for the rest. Commonly, feed-forward is used in flywheels to where, say, we have a motor that at max output is 6,000 RPM. Well, if we want it to go at 3,000 RPM, we know we can usually set it to 50% output and get pretty close in the ballpark, but then we can have the control loop correct for the rest. My last slide is motion magic. Now this is where we have smooth motion from point A to point B. You can see this blue line here is really curved. Now, whenever we set the set point is represented by this dashed line here. The motion magic controller says, oh, we want to go from point A to B. We are going to take this really smooth motion by slowly accelerating and building velocity, hitting a cruise velocity, and then decelerating back down to the point. Now, this is really forgiving to the robot instead of jerking the robot around and breaking something. It also looks really cool. And the thing behind this is a trapezoidal velocity curve. You can see the velocity is represented by this black line, and it is in fact a trapezoid. Now, Motion Magic is available on the Talon SRX, the Falcon, and the Neo. So it is not that hard to use, and it usually looks really cool. Thank you guys for listening.